Welcome. Today we'll be building a binary AI model. This is an artificial intelligence that creates yes-no outputs. Specifically, the model we are building will be able to determine if a tumor is benign or malignant based off of characteristic data it has available. It is built using 12 lines of Python code, and I'll be going into each of these lines and explaining what it is, does, and how they come together to build our overall model. You will need the cancer.csv file from the Center for Disease Control, available by clicking the link in the description and download it from my GitHub. To begin, we'll be using a browser-based coding tool and the GPUs run by Google. This is free so long as you have a Google account, and we'll open a web browser and go to collab.research.google.com. And once you sign in with your Google account, you'll be greeted with this open notebook page. Now we'll start by clicking New Notebook on the bottom left, and then once it loads, we'll go on this left-hand column and click this folder. Then under Files, we'll click Upload just below it. Select our Cancer Excel sheet, open it. We can clear this warning since we uploaded it, we know it's safe. And then you'll notice after we uploaded that, we're now connected to a runtime hosted by Google, so we're going to be using all of their assets. And your computer stats really won't matter because we're going to run it all off of theirs. Now, we're going to click into this bar next to the play icon here, and we're going to work on our first line of code. And it starts with import space pandas as PD. Now, import allows our model to access a module. Now, a module is a vast library of code that we import either entirely or just as part of it. Like checking out a entire book or just being able to check out a chapter or a specific sentence. In this case, we're importing pandas, which is a one-dimensional labeled array capable of holding data of any type: integers, strings, float, Python objects, etc. Comment below if you'd like me to expand on different arrays and when we use them. Completing this line, we set an alias PD to reference pandas. And we're going to use that alias in our next line, which is going to be dataset space equals space PD dot read underscore CSV parentheses single quote cancer.csv. All right, you'll notice that it completes our single quote and our parentheses there, which will save us a lot of time in the future. And essentially what we've created is by invoking dataset, we're telling our model that we're creating a dataset array. We make that dataset array equal to pandas, which we call on with PD, specifically the read function of pandas, which allows it to store and read a CSV that we specify there, and that's what Excel sheets get saved as. And then we point it to our cancer.csv, which is in our data store here. Now we'll hit Shift Enter and check for any errors, and it looks like we're good. We can tell that by the green check mark. And in our new cell, we're going to start our next piece, which is going to be focused around the two foundational variables of our AI model, which are going to be X, which equals all of the data in this Excel sheet from here all throughout. And the way we're going to do that is by telling it to cut or drop, in this case, the diagnosis column. Now we do that with X space equals space dataset dot drop parentheses columns equal to bracket. Now brackets tell our AI model that we're going to be inserting a string. And our string is going to be double quote diagnosis, if I can spell that, diagnosis parentheses 1 equals M, comma space, 0 equals B. And again, it completes our parentheses, double quote, bracket, and our other parentheses. So Setting a variable x, we make it equal to dataset. Now this calls on that first cell's variable we set up here, and we use the dot drop function to drop or remove the diagnosis column. And you can see that string reflected here in the Excel sheet where 1 equals M, 0 equals B. M for malignant, B for benign. If we only put diagnosis, our AI model would think we just want to drop this little A1 block right here. But since we specified this string, it's going to tell our AI model not only that we want to drop this, but it's also going to, because of pandas, associate the column title with the row data. And that's going to come in handy later and save us a ton of coding. So we've set the X variable, we'll hit Shift Enter, check for errors, looks like we're good. And now we'll set the Y variable, Y space equals space dataset, bracket, double quote, diagnosis, parentheses, 1 equals M, comma space, 0 equals B. All right. So just like in the above, we're calling on the dataset Excel sheet and selecting the column diagnosis. Ba-bum, using that same string. All right, now we'll hit Shift Enter, check for errors, and create a new cell. Oh, looks like we got an error here. Spelling is important, so we'll change that from diagnosis to diagnosis. And go ahead and run that, and we've cleared the error. Perfect. So in that new cell, well, to wrap up, so far what we have is an AI model with access to the Pandas module and a way to split the data of the tumors in the Excel sheet to the diagnosis, Y, and all of the data characteristics that make that diagnosis separated over into X. Now, we'll begin this cell by first selecting a specific function from sklearn and importing it. So from sklearn dot model underscore selection import space train underscore test underscore split. Now it almost reads like a sentence, but to rearrange it so it makes sense, we are importing the function train test split from the model selection library of sklearn. Now we'll enter down. Oops, I gotta click back in. There we go. We'll enter down and we're gonna create a new line. We're going to create a new line where we create these train and test variables for the train test split. Now, to specify, we need to split this data in the Excel sheet into training data that the AI model will learn and build confidence with, and the testing data, which we feed to the AI model, and it will see it as new data, giving it its best answer in real time. So on this new line, we're going to create these variables: x underscore train, comma space, x underscore test, comma space, y underscore train, comma space, y underscore test, comma, no comma, equals space train underscore test underscore split, parentheses, x comma y, comma space test underscore size equals 0.2. All right, so what we've done is we've told the model to, we've told the train test split function two things. First, that the variables for train and test are split into x and y. Second, that the test data size is 20% with this 0.2. Now the model will automatically split the data from both x and y variables we made earlier into 80% training data and 20% testing data. and assign the correct portions to the train and test variables that we made up here. The x and y train and test variables are vital for creating the separation between learning data and data it has to respond to. So we'll hit Shift Enter and create a new cell. It looks like we got no errors. Perfect. So in this next cell, we're going to import the TensorFlow model or module to leverage the sequential Keras models. So we do that with import TensorFlow as TF. So much like our first line, we're setting a variable for the module that we're importing. And then we're going to use that in the line right below it with model equals tf dot keras dot models dot sequential, oops, capital S, sequential, and then parentheses. Now the parentheses remain empty, and I'll go into that in just a moment. So what we did is we named the sequential model that we want out of the Keras models library within the TensorFlow module. And this parentheses, because it's empty, it basically says that we're going to start a new instance of this. And we want sequential model. We want sequential model because our layers will need to be added and processed in order. So layer 1 goes to layer 2 to layer 3, and there's no mixy-matchy. So we'll hit Shift Enter, check for errors. All right, took a moment, but looks like we're all good. And then on this next cell, we're going to make the layers of the AI model, essentially the brain of our AI, where all the magic happens, all the complex math and stuff. There will be 3 layers to this, and each line will create one of the layers. Each line starts with model.add parentheses tf.keras.layers.dense with a capital D. Now what you can do is you can highlight that, Control C to copy, then click out of that parentheses, enter down, Control V to paste it, enter down one more time, clear out those little tabs there, paste it again, because each of these layers is going to be a dense layer. And these dense layers come from the Keras within the TensorFlow. And we're adding that model. So it almost reads a little backwards, almost like we're talking like Yoda. So now we'll go back to that first line. And you see we use dense layers because we want each point of data in our data set, in our data sheet. So each one of these is going to be an input into the complex math of the layer. So each node will be grabbing from each of these little data points here. And I'll go into more detail after we complete the layers. So picking up on the first line after dense, we'll do parentheses, 256, comma, space, input underscore shape equals x underscore train dot shape bracket, because we're going to give it a little string there, 1 colon, and then outside of those brackets, we'll do a comma, space, activation equals single quote sigmoid. And then we'll double check that line. Everything looks good. If there's any issues where you've got like a parentheses with no end parentheses, you'll notice that it becomes red, like on this second layer. So now our first layer has 256 nodes, which will grab the data points from the Excel and put them through the complex math to shape it before passing it to this second layer. Now, adding more nodes does increase the model's capacity to learn complex patterns in the data, which can be beneficial up to a certain point. However, too many nodes can lead to what's called overfitting, where the model performs really well in the training data, but generalizes and does poorly on the test data. So using 256 nodes in our hidden layer here provides a good balance between model complexity and performance. However, feel free to experiment with using different numbers of nodes to see for yourself how they affect the model's performance on our dataset. So the input shape, this input shape x underscore train dot shape, and then the 1:, means we want all of the data in the xtrain variable, which is going to be 80% of the x variable that we set higher. And that's what's going to be used by the nodes. And then by ending with activation equals sigmoid, that tells the layer what shape the data is going to take. And the sigmoid is a mathematic function that squashes our outputs to zeros and ones. So that's what's going to be passed to our next layer. And on the next line, we're going to pick up again after dents, parentheses, 256, comma, space, activation equals single quote sigmoid. And then we'll go outside this parentheses here and add one more. And you see it turned this one green, completing that little thing. And then this creates another layer with 256 nodes using the same complex sigmoid mathematic function for the first layer nodes to pass their information to. And on our final line, we'll do parentheses after dents, 1, comma, space, activation equals single quote sigmoid. All right, notice that this layer only has one node. Oh, let's put that parentheses there so we don't forget. It only has one node. And this is because all the processing and equation that's going on between these two layers is finally going to be passed to one singular node that will put the final output towards our answer layer, as demonstrated in this slide here. So you see the xtrain data is going to get shaped by this layer 1 node and then passed to the layer 2 node where it's processed, and then passed to the layer 3 node, which squashes all of that complex math into a final 0 or 1 output by the sigmoid activation, which that output is then passed to our answer layer, which is going to be made with Shift Enter here. And it looks like we're really good on the no errors on that one. And so remember, capitalization and spacing matter. So that's usually the most common errors, or like commas. And when you do generate an error, usually it's pretty helpful. Like for instance, if we took this comma out and then we tried to run it, it'll show a little tack here showing that, hey, perhaps you forgot a comma. And then we do comma, run it again, and boom, we've solved the error. Okay, so in the next cell, we're going to start building our answer layer. And we're going to do that. We're going to do that because this layer acts as like a teacher helping the nodes to optimize their complex formula, creating correct assumptions. And we need an optimizer for that. So we'll get that from model.compile parentheses optimizer equals single quote Atom, and then outside that single quote we'll put a comma, space, loss equals single quote binary underscore cross entropy. Then outside that single quote, we'll do another comma space, metrics equals bracket, because this is going to be a string, and we're calling on the internal string of the model, accuracy. All right, so a compiler is used to configure models for training. We specify we want the Atom optimizer because it adapts the learning rate of each training session, eliminating repeated mistakes and refining the weight and confidence of all of the variables and equations that these previous layers are passing to it. And we set the metric for accuracy So that way, the goal of the optimizer is to create more and more accurate results from this layer to the answer layer's answer, which is basically, to sum it up, the answer layer is our diagnosis. And then the previous layer, the guessing layer, is made up of all of this data being passed through that sigmoid function right there. And that's described a little bit better in this slide here. So that layer 3 of the guess node, or the layer 3 of our hidden layer, passes that final one node output to the Atom Optimizer, who compares it against our diagnosis column. Then the result of that is passed back to the Atom Optimizer, which passes it down to develop the model confidence. And then that whole cycle repeats each training session. Now we'll hit Shift Enter, check for errors, and looks like we've got one. A spelling error, classic. Model, perfect. So now we'll go into this next cell. Okay, so far we have a model with access to pandas and TensorFlow modules that can parse the data into different slices for training and testing to form increasingly accurate estimations on a tumor. However, it is untrained and would return very poor guesses right now. So we'll build a training layer, and we do that with model.fit parentheses x underscore train, comma space, y underscore train, comma space, epochs equals 1000. All right, so in Keras and TensorFlow, model.fit tells the model how to train itself on the dataset, which is going to be the X train and Y train data that we split off from the Excel sheet before. And we set the epochs, which means training sessions, to 1000, giving our model 1000 tries to create the most accurate algorithm to be used in the test later. Normally, the number of epochs will be based off of complexity and the resources available, but you can set the epoch number as high or as low as you want, and you'll notice the differences for yourself on how accurate it becomes. Now, let's run each cell from the top and let our AI train itself. So we run each of these, all good. All right, so you can see it's going through the epochs, and the accuracy is a little variable, and you can see it's getting slightly better, slightly worse, and that Atom Optimizer is doing its job and starting to create a more and more refined. So it's like, oh, with this data put into here with this equation, I'm getting a little more accurate, but when I change the data with the same equation, I'm getting less accurate. So then the problem is the equation, it starts to modify the equation and rinse and repeat. And you can see on this side here, it's like 96, 97, 88, and it'll go for 1,000 times. And it does go pretty fast. It will take a couple more minutes here because we're at about 700. Go AI, go. Getting more accurate thanks to the optimizer. All right, we're almost done in the final stretch for 150 more training sessions. And getting in the last one. Looks like it's, there we go. And it ended with a 95% accuracy. Excellent. So now we'll come back up here. Okay, so now we can see that that final epoch put out a 95.8% accuracy. But as you can see, it's had more accurate sessions before. So just because this was the last one doesn't mean that it's the one it's going to choose. Because we set our optimizer metrics to accuracy, it's going to go through these 1,000 epochs and find the most accurate one, and then use that equation formula. And it's really complex, but luckily we don't have to worry about that. So we'll scroll back up to our code. Oh, scroll on the far right hand one, or otherwise you're just scrolling through that. and then we'll hit Shift Enter. Oh, and it's running it again. My apologies. We can go ahead and come back up here. Well, actually, an easier way is if you delete that, now we'll have an error. Perfect. A purposeful error. And we'll go to this final line. Well, we're going to create the final line of the module, or of the model. And this is where the new data gets processed to the using the complex formula that it chose for the most accuracy out of all those epochs. Now, it's pretty simple compared to all the other lines. It's simply model dot evaluate parentheses x underscore test, which we made before, y underscore test, and make sure our parentheses are closed. Beautiful. So this is going to be that 20% of data that we split off as test data from the Excel sheet. We'll hit Shift Enter on that one and check for any errors. And it looks like we got all the errors out. And you can see that it has done 4 out of 4 tests. And the example loss resulted in an accuracy of 98%. So it's pretty darn good. So it can tell you whether it's a malignant or benign tumor with a 98% accuracy. Well, I hope you enjoyed the video. Be sure to like and subscribe for more videos and comment below with any questions or suggestions. And remember, AI is only as good as we make it. Farewell.